Let's formulate the problem. I have a signal. It sounds a little like this. And then I have a sample. I chose a piano piece, but it could be any kind of noise, and it sounds a little bit like this. And hidden in that sample is my signal, and I want to recover that. I want to look through my sample, and I want to see, hey, is the signal I sent out in there? How am I going to do that, especially when the graphs of this sample and signal look a little bit like this? It's not super clear. So what I'm going to do is use a process called correlation. And correlation in digital signal processing is defined like this. There's also a variation in continuous time, but that's not as important for DSP. And what basically you're going to do is So I wrote some code and I did it. And this is the cross correlation computed using NumPy's correlate function. You can see around 31 seconds in, there's a pretty good match there, but there's a faster way to do this. It turns out that correlation is just convolution, but one of the signals is time reversed and the complex conjugate is taken. We're working with purely real signals here, so we can drop the complex conjugate part. We all know well by now that convolution in the time domain is equivalent to multiplication in the frequency domain. So what are we going to do? We're going to take the FFT of one signal, the FFT of the time reversed other signal. We're going to multiply those two together piecewise, and then we're going to take the inverse FFT, and we're going to get the output. And you can see it looks just the same, accounting for the indices. I should add in here that there's a bit of a difference when using convolution because of the way convolution uses indices. The length of a convolution is greater than the length of just the correlation. But once you account for that, you can see it looks just about the same. You might have noticed the values in correlation get very large very quick. So if you really want to get useful results out of it, you have to normalize it somehow. There's three main ways. You could normalize it to a z-score. You could normalize it by the magnitudes of each of the signals, or my personal favorite way, you can normalize it to the magnitude of the autocorrelation in the signal. The autocorrelation at 0 lag will give you the greatest correlation possible. So you divide by that and you get just a relative measure of how well they match. And you can see at the very bottom here, it matches pretty well. We get a correlation of around 0.8 or so. I'd say that's pretty correlated. We probably found our signal. So why don't I have a project? It's because of this little guy and how damn hard they are to work with. First, I thought I was going to be able to take sensor readings using a microphone from the environment and see if I could match signals, maybe like a bird call or something. Turns out I had a really cheap microphone from China and it just didn't work. So then I thought I'd write a simulation in Python that would periodically, every now and then, a couple, 8,000 times a second, send a value over serial to the Arduino that would mimic a signal with noise, and I could run it that way. But serial's really slow. The Arduino kept losing data. It would just get complete junk values, couldn't replicate a signal at all. So then I thought, hey, maybe I'll just ignore the time part and we'll just handshake, we'll just ask for values. The Arduino couldn't really do that either. The code was so slow, I was only getting about 600 or 700 samples a second, which when just the signal is almost 3,000 samples is just not viable. And then I thought I could live with that though. And then I ran into the real problem. I was using the Arduino FFT library that I found to try to compute Fourier transforms, but I ran out of memory. I need just a buffer alone for the signal of 4096 bytes. No, not 4096 bytes. 4096 times 4 bytes or so, whatever the size of a double is. And the Arduino just doesn't have that memory. So I don't have a project, but I tried. You can see the code, it's there. This is like take 5, and I'm so close.